All right, let's talk about circles. Circles are perfectly round objects like this absolutely perfect circle that I drew here. Flawless in every way. So, kids, circles are round. Step one, circles are round. Write that circles are round? No, I don't think you need that. Well, some of you might need that in your notes, but I'd say in general, probably no. But I would draw a circle because I'm about to label a bunch of pieces of this one that you may want to have in your notes. Okay, so I just drew a line going from a dot in the middle of the circle all the way out to the edge of the circle. And there's two things that I want to label here. The first thing that I want to label is the dot that I started drawing from. What's it called? The center. Very good. I'm going to call the center point K. K stands for center. And we're going to say it goes out to point N. So we would say that segment KN is a radius. And we would spell radius correctly. Radius is RAD, not RDA, as I just wrote. Now, a circle can have more than one radius. In fact, how many radii, which is the plural of that, how many radii could a circle have? It could. You're right, a lot. How many is a lot? As many as you want. So KL is also, it does not depend on the size. You can draw as many radii as you want. And this will not blow your mind. It will not blow your mind so hard you may not even want to write this down, but all radii are congruent. Shouldn't blow your mind that a radius going in one direction is the same length as a radius in another direction. In fact, let's just make it official and put the little diddly doos on there. Radii, RADII, is the plural of radius, which is pretty disappointing because radii is a fun word, but radiuses would be way more interesting to me. So all radii are congruent. The symbolic way of writing that is that we could say KN is congruent to KL. I do really like circles. I like triangles the most, but circles probably my second favorite. The sir what now? What is circumference? Sounds like a really fat knight. King Arthur and his Knights of the Round Table. Lancelot, circumference. Circumference, the most rotund of the Knights of the Round Table. What do you think would happen if I slapped together two radii and sent them veering off in opposite directions? Nothing would happen. That would give me what is called the diameter. So I'm going to call this DEG. And so we would say that EG is a diameter. And this is something that you should know already, but we'll put it in our notes just for the sake of completeness, which is that the diameter is equal in length. The diameter is the same length as two radii. Symbolically, we would say that ED times 2 equals EG. A radius is half a diameter, or a diameter is double a radius. So a diameter specifically is a line that goes through the circle and specifically has to go through the center of the circle. Oh, if you wanted to do like diameter has the same length instead of is the same length, that's fine. If you like the word has better. What if I have a line that does not go through the center, but does go from one side to the other? For example, something like this.
That's just called wrong.
It's not called wrong.
It's just called a weird line that shouldn't have been there in the first place.
Well, that is a very long set of words for what we could just say in one word, which is chord.
Chord?
Yep, chord, just like a piano chord. So the definition of chord is a segment with both endpoints on a circle. So here's my question. Is the diameter a chord?
Yes.
Yes. Because it is a segment with both endpoints on a circle. So we could say a diameter is a chord that passes through the center, which is probably not exactly the definition of diameter, but it's probably close. Passes through the center of a circle. I'm sure the official textbook definition probably uses more flowery words than that we can't understand, but I'd say in general, that's a pretty solid definition of diameter. The length of a diameter is 2 radii. That's how you figure out how big it is. But how would you actually describe a diameter? It's not just a line that goes through the center. It's a chord that goes through the center. What's the difference then? Why am I specifying it's not a line, it is a chord? What would be different about a line versus a chord?
Because a line doesn't have this points like
Say that again, Peyton? That's exactly right. A line doesn't have endpoints. The line just keeps on going. The chord specifically stops on the circle. You can see why it would be a problem if the diameter was a line. How big's the diameter? It'd always be infinite if it kept going forever. It's got to stop on the circle. Although that would make finding diameter much easier if the diameter was always infinity, I suppose. Okay. Let me draw another completely flawless circle. It's super flawless. This time, I'm going to draw a line. It can be a line segment, or a ray. I'm going to draw a line specifically. The greatest ray of all time, Ray Stevens. Shout out to Ray Charles. Ray Charles wrote.
Are you just skimming the top of it?
Yes, oh, that is such a good word. She said, are you just skimming the top of it? A chord intersects the circle 2 times on either side. On the edges of the circle, a chord intersects 2 times. This only intersects a circle 1 time. When you have a line that only intersects a circle 1 time, it just I love Peyton used the word skim. That's a perfect word. It just slides right along the top. It just barely touches it 1 time before sailing off into the ether. This line is called a tangent.
No, not more tangent.
A tangent line intersects the circle at exactly 1 point. I shouldn't say intersects the circle, intersects a circle, because there's more than 1 circle in the world, kids. Intersects a circle at exactly 1 point. Now, if you look at this super cool, perfectly straight tangent line I drew, touching my perfectly round circle, where's the 1 point that it touches my perfectly round circle? R, and we have a special name for R. It's called the point of tangency. I say close because since a tangent line intersects once, it is a point of it, the point of intersection. But we want to be very specific that it's a point on a tangent line. So we call it a point of tangency. But you're right, it's where it intersects the circle. You're giving me the definition that a normal English-speaking person would say, and I'm giving you the definition that a psychotic math person would give. Like the crazy chemistry lady, except I'm crazy math lady.
The crazy British
Please don't assume my gender. I am crazy math lady. Not gonna be confused with Sierra's mom, who's just crazy lady.
No, she's crazy about Harry Potter.
No, like on her lunch order, she writes crazy lady. I wasn't calling her mom crazy. Her mom calls herself crazy. So this one's not a segment, so it isn't a chord, and it touches the circle twice, so it's not a tangent line. What could it be? I'm not telling you. Okay, I will. I'm going to put the center on here to specify that it can go through the center, but doesn't have to. This line is called a secant. A secant. A secant intersects the circle. Oh, let me be specific because it's not a segment. A secant is a line or ray. Because if it was a segment, it would not be called a secant. It would be called a chord. If it's a ray or a line, meaning it touches the circle and then exits the circle, that is a secant. Intersects a circle at exactly 2 points. What's it called when a line intersects a circle in 3 points? Yeah, it's called not a line. You can't intersect a circle in 3 spots in Euclidean geometry
Unless it's like
with a line.
that sounds like fun. It's not a line then.
You probably could do it in non-Euclidean. In fact, I'm sure you could do it in non-Euclidean geometry.
Like anything in non-Euclidean.
You can do anything in non-Euclidean geometry.
That's how Euclidean.
Parallel lines touching, triangles that have more than 180 degrees, dogs and cats living together, mass hysteria.
This is what are we ever going to learn non-Euclidean?
Are you ever going to learn non-Euclidean geometry? I hope so. It's really cool. Are you ever going to learn it from me? No. No, you are not. I'll give you some non-Euclidean geometry fun facts every now and then.
You should make a summer class.
Yeah. Oh, sure. I bet that would be well attended. Hey, kids, come up here in the summer to take a non-Euclidean geometry class. Yeah, I bet that would be well attended too.
I'll do it. So why? Nothing better to do.
So one thing that you should know about circles is this: all circles are similar. Remember, similar means same shape, but not the same size. So it makes a whole lot of sense that all circles would be similar because all circles look like circles. You can't have a circle that has different angles than another circle because the Mandalorian. Why is the Mandalorian in here? Is that Arthur Morgan now? Arthur, I'm going to mute you. You're not even in geometry.
Oh, that's his name.
Okay.
The Mandalorian.
That's
Shelby. The upgrade. Arthur Morgan.
there we go. All right. So let's talk about what happens when we combine some of these that we've learned: tangents, radii, diameters, secants, that sort of thing.
I have
Yes.
Can we use tangent, cosine, or sine
Uh-huh.
in circles?
Uh-huh. That
No.
is such a good question for you to ask. I'm surprised no one asked it when I wrote the tangent line first. You're like, wait a second. Tangent is the ratio of opposite to adjacent, and now we're reusing the exact same word to talk about something completely different. But is it something completely different? No, it's not. In fact, don't put this in your notes because we're not ready for it yet. But if I went up here to the tangent line and I were to draw a radius going to the tangent line, that by definition intersects at a right angle. A radius will always intersect a tangent line at a right angle because radius just goes to the edge of the circle, which is where the tangent line touches. So a tangent line is always perpendicular to the radius. Can you see how we might be able to get a right triangle out of that? And what are the pieces of this right triangle? If I use this angle of the right triangle, what are the pieces that I have? Well, it looks like I've got the opposite and the adjacent, which is the ratio of a tangent. Ba, ba, ba. Okay. We're gonna do geometry, but with wizards.
Question, are they regular wizards or are they math wizards?
It's geometry. What do you?
Geometry wizards.
Okay. So I can combine two radii together, just like this, and I create an angle. Look at that, I made an angle. Here he is. Oh, he's so cute. It's an angle made up of two radii. Since the angle that I just made is at the center point of the circle, which in this case we call F, since it's at the center, we call it a central angle. A central angle has a vertex at the center. And its sides are the radii. So cool. So in this case, EFG is a central angle. Yeah. Yeah, it's amazing.
Will we ever go over ovals? Will those ever be-
Yes, ovals will be in algebra 2, except they're not called ovals. Close.
Squished circles.
Yes, that's the official math term, squished circles. That's not till algebra 2. So Tucker can inform you all about them. Well, not yet, but he will be able to eventually. Okay, so when we make a central angle like this, the central angle sort of captures a piece of the circle inside of it. This piece right here. It kind of looks like a pie piece. And if this was a pie piece, the crust of the pie is called an arc. An arc of a circle is part of a circle between two endpoints.
Does that mean the opposite side of the circle, opposite end of the circle is also an arc?
That is such a smart question. If I said arc EG, and the way I read it is like this, how do you know that arc EG is the part that I highlighted and not the huge part going around the other direction? Such a good question for you to ask. You're so smart. EG is what's called a minor arc, which is less than half of the circle. If I wanted to do the big piece, that would be called a major arc, and I would need a third point. Like I might put a point over here called H. And then I would say EHG is a major arc. This is more than half a circle. And you need 3 points to name this one. Because if I only used 2 points, I would be saying connect the shortest distance between those two. And if I have 3 points, well, to go through all 3 points, I would have to go all the way around. I can't do EHG without going the long way. It's an arc. If you want, I guess. It's not what it's called, but you can call it that. I mean, you can call it Frank if you want to. It's just not his real name. So a minor arc is when it's less than half. A major arc is when it's more than half. What do you call it if it's exactly half? Semicircle. Very good, Ellie. Exactly half is a semicircle. You could also call it a semicircle if you tried to draw a circle and you weren't very good at it.
Oh, so it's yours.
Hey! No, not like mine.
Exactly.
The opposite of mine.
No, we were going for it. You wanted a stencil. Yeah, you.
Why would you think that?
Because you set yourself up for half of these.
No respect.
He does one for every single
No
one. He opens
respect.
the door and says, "Come in." And then gets upset.
Yeah, but sometimes I literally open the door for you at the beginning of class and say, come in, and you will immediately start roasting me, and it hurts.
You do it
I'm like,
twice.
hey, come on in. You're like, no, I hate you. So rude. So rude. As my 4-year-old would say, be nice. We don't use words like that. See, she knows. She's 4 and she knows live in harmony and try to love one another.
When she grows up, she's probably not going to live by that.
Yeah, whenever she grows up, she'll be roasting you along with us.
She'll probably also be roasting Mrs. Taylor.
Nobody roasts Miss Taylor. That's just how you get killed.
True.
Nobody roasts Mrs. Taylor. That's true. I could just imagine how awful that would be. We do not talk like that to teachers. Yes, ma'am. She ends all of her sentences in yes, ma'am, because that is the only thing she wants to hear from you.
Oh.
When she asks questions, she ends her questions with the thing that she wants you to say back to her. We are not going to act like that in this classroom. Yes, ma'am. And the kids go, yes, ma'am.
Do you also say that?
Yes, he
Yeah,
says yes.
she does the
ma'am.
same thing to him.
She doesn't do it to me, but she does it to our kids.
Liam doesn't count.
She still says it to him. She's got to train him. Plus, ma'am sounds like mama. She really wants him to say mama before dada. So we are going to use what is called the arc addition postulate. The arc addition postulate is going to blow your mind. It is. Uh-huh. Is it where there are arcs? Is there a postulate involved? All true. Now, arc CE, which is a minor arc, is this guy. Arc ED, also a minor arc, is this guy. If you had to guess, and you do because I haven't told you how to do this, what would you say is the sum of those two arcs? CED, very good. I have to use 3 letters to name it because it is a major arc. CED is more than half of the circle. If I just said arc CD, I would not be talking about that. I would be talking about this. This is arc CD. So I have to put the E in there because it is a major arc. Also known as frowny faces.
No, the whole face is upside down.
Got her.
I'm trying to be positive. I could have said frowny face, but it's not.
It looks like an upside down smiley. You're really trying hard to be positive there.
It's the thought that counts. Yeah.
Dr. Winger, just tell us the prognosis. Well, the patient is not unalive. Wait, what?
Not dead yet.
I'm not going to lie to you. This harkens back to the transversals problems that I really, really love, where you get like one angle, but you could use your postulates and theorems to figure out literally everything else. I really like these circle problems for the same reason. You get a tiny little piece of information. Oh, sorry, I didn't give you enough information.
Yeah, where the heck's the F?
Sorry, I forgot a really important angle here.
How did I keep up with that?
Where you get a tiny little piece of information and you are able to figure out every other piece of the circle. Now, the measure of an arc and the measure of its central angle are the same. We're keeping things simple. We say the included arc, meaning the arc that is inside of that angle, or that is bound by the endpoints of that angle, if you want to impress the ladies at the math party. So when I see that angle ABC is 50 degrees, that tells me that arc AC is also 50 degrees. No fancy math involved. Central angle and arc are the same. Now, if it's not a central angle, which we haven't learned about yet, but we will. If it's not a central angle, all bets are off. They are not equal. It's only central angles. Okay. So what else can you figure out? DE? How big's that one? How do you know? Very good. I heard the magic word. These are vertical angles, which means arc DE is 50 degrees. Hey, we found one of them. The measure of arc DE is 50 degrees. Cool. Keep going. What else can I do? I suppose I should specify, because even though my picture is flawless, we should specify those are diameters so that you know for real that those are central angles. B is the center.
Wouldn't EF,
No, keep going. Arc EF, how big is it? 90. This is a 90-degree angle. So arc EF is 90 degrees.
wouldn't ABD be 130?
Why?
Because that
Very good. ABE is a diameter, which means it's a line, 180 degrees. If this side is 50, it means the other side is 180 minus 50, which is 130. Excellent job, Peyton. I'm only missing one angle. How do you know it's 40? Yes, I'm listening. You said this angle right here is 40. It's complementary. ABF is 90 degrees. So that'd be complementary. The other way that you could figure it out, which is not as easy as complementary angles, is by subtracting all the angles you already know from 360 because the circle has 360 total degrees. So that would work also. Okay, so let's see if we can figure out our last two angles or our last two arc measures that we needed to know. We needed to know arc CE. That was another thing we were asked for. That requires the arc addition postulate because CE is right there. That's going to be the measure of arc CF plus the measure of arc FE, which we figured out. CF is 40 degrees.
Could it also be 3? No, 130?
Yes, it is 130. I was just writing it out the long way, showing how we got 130.
Thank you. Just flip it over.
You're right. I was just doing it the long way. And then finally, we need the measure of arc FAE. So FAE is a major arc. FAE. And Emily says 270, which is correct. There are two different ways you can get this. What are they? Good. You could take the measure of the entire circle, which probably just like circle B, which is 360, minus the measure of arc FE, which is 360 minus 90, which is 270. Or can I slow down real quick?
You could add all the things except FE.
Now, Emily's way clearly is faster, but you got options. What else? What?
What else do we have to do today?
Brush your teeth, probably. Take a shower. I'd eat lunch if I was you. Shouldn't skip meals. If you mean what else are we going to learn in our introduction to circles, the answer is nothing. We're just going to learn the basics of circles today. But next week we're going to start adding in some angles that are not central angles. Those are called inscribed angles. And then we're going to start adding in angles where the vertex is not even in the circle.
What?
The vertex is outside the circle and two secants make up the sides of the angle.
Oh gosh.
Those are pretty cool. And then we're going to start using tangent lines to make
Tangency.
to make inscribed shapes and circumscribed shapes, like if you drew a triangle and then put a circle in the middle of the triangle, or vice versa.
Ooh, fun.
Yeah, sometimes. Sometimes they're fun, and sometimes they're awesome. Your face is a nerd.
Oh.
Does anybody have?
He had to hesitate and stutter on that.
Does anybody have any questions for me about this? Questions besides, how do you keep it so gangsta fresh, Mr. T?
No.
Nope,
That was my only question.
that was your only question. All right.